All right, let's move on and talk a little bit about sorting. So we can sort things. In fact, there is a predefined sort operation, but it's not in the prelude. It's in something called the list collection. So there's a bunch of more elaborate functions collected in data.list. And there's a sort function in that collection. So we can import just that function and we can sort some lists, and we indeed get what we would expect. So the sort function, what is its type? Well, it doesn't just apply to numbers. Here I'm applying it to a list of characters. What else could I apply it to? I could apply it to a list of strings, which is of course a list of lists. Oops, that should be a string. And it sorts those as well. Okay, so what's the type of sort? What do you think the type of sort would be? Takes a list of anything and gives you back a list of the same kind, but of course sorted. Does that seem reasonable? Well, not quite. You can't sort unless you can compare, right? You can't sort things unless you know how to say when one thing is bigger than another. So the minimum requirements on the type is that it has comparison operators, and that's the class ORD. So if we ask what the type of sort is, it says, yes, it will sort a list of anything and give you back a list of anything, but the anythings that you're sorting have to be in the ORD class, because you have to be able to compare them. So you can think of this as the basic type, and this is a kind of constraint on that type. Okay? It says, for all types A, for which A is in the ORD class, this function takes a list of A and produces a list of A. Okay? So let's define some of our own sorting functions, and we can take some classic examples. And one that I showed you, maybe if you looked at the introduction to this, was quicksort. No, actually, yeah, let's start with quicksort. Quicksort's interesting because the recursive pattern in quicksort is a little bit different from the recursion pattern we've seen before. In the recursive pattern we've seen before, we do a recursive function on a list of this big in terms of what happens when you compute over a list which is that little bit smaller by sort of taking off the first element. Quicksort doesn't quite work like that. It works recursively on smaller lists, but the smaller lists are computed from the bigger list in a slightly different way. So do you all remember roughly how quicksort works? Most of you remember. The idea in quicksort is you take an element from the list you want to sort and you sort of plonk that down in the middle. Then you put all the things which are smaller than that guy on one side, all the things which are bigger than that guy on the other side from the original list, and you recursively sort the two sublists. And you keep doing that recursively, and then in the end you will get a sorted list. So the base case is still the usual. Quicksort for an empty list will be an empty list. If you want to sort a list that starts with X and continues with X's, what we'll do is we'll use this as the so-called pivot element. That's the element that you put it sort of in the middle. So X will be in the middle, so to speak. And on the left, we will let's just call it qsort. I can't be typing quicksort every 5 minutes. Let's say we qsort the smaller elements on the left, put X in the middle, and then we quicksort the bigger elements on the right. And what are the smaller and bigger elements? Well, they're computed from this list, but they're not literally that list, right? So what are they? Well, the smaller elements will be the list of all elements y, where y is taken from the rest of the list, and y is less than x. Less than x. Okay, so they're all the smaller elements. And the bigger elements, or the bigger elements, are those elements, let's call them Z, where, key map change, I've gone Swedish, that's better. Where Z is also taken from that list of x's, but in this case, Z should be greater than or equal to x. So we can have more than one. And there we have quicksort. Let's just check. Property of quicksort, if we have a list of x's, should be that sort x's is equal to, that would test whether our definition is the same as the standard one. And let's make this a list of booleans. My claim I made earlier is true. And let's just quick check prop of quicksort. And it seems to do the right sort of thing. Okay, any questions about that? It's slightly unusual. There are two recursive calls, not one. But in each case, the list that we're doing recursive sorting on is smaller than the list we started with. And that's how we know that this will terminate. We start by we want to sort a bigger list, and we do that by recursively sorting smaller lists, but they're not just the simple smaller list, the immediately smaller one. They're computed by picking out, in one case, the smaller elements than x, and the other one the bigger. Yeah?
Do you know what kind of sorting algorithm the standard sort?
I think the standard sorting algorithm uses a form of merge sort because it has a more reliable complexity. So quicksort in the worst case is order n squared, whereas merge sort will always give you order n log n. So I would expect merge sort is probably the one that's used here. Now this isn't, so when I call this quicksort, it's in some sense like classical quicksort, but part of classical quicksort is the fact that quicksort is what's called an in-place sorting algorithm. It's an imperative algorithm. You have an array of things and you sort by shuffling them around inside the array without using any extra space. The Haskell version here is abstracting away from all those details. So it doesn't, we can't claim that it has that property of classic quicksort. The space behavior will not be classical constant space. Well, at least there's no reason to expect it to a priori. It's a very different beast in a functional setting. Okay, we'll get into those kind of issues a little bit later in the course. Okay, let's take another example, and that's one which is a little bit simpler in terms of its recursive pattern, and that's insertion sort. Not a very efficient algorithm, but insertion sort is rather like quicksort. The base case is very simple, and in the recursive case will be the classic one. We compute sorting a bigger list in terms of sorting the smaller list. So if I've got a list of things I want to sort, and I know how to sort slightly smaller list, how do I get the sorted big list? Well, I need to take that first element and I need to insert it in the right place in the sorted smaller list. So the key operation in insertion sort is indeed insertion. So we need to insert the element x into the list we get by sorting the rest of the list. So then the key operation, inserting an element into a list, is an operation, well, what type does it have? We take an element of type A and a list of A's which we assume are already sorted, and we produce a slightly bigger list of A's by inserting this A at the right place in the sorted list so that the list remains sorted. So what's wrong with that type? Yes, we need an ORD constraint, because insert, in order to insert the element in the right place, needs to be able to compare the elements in the list. So for an ordered type A, then it has that type. Okay. So what is the insert definition? Okay, well, we're going to insert X into an empty list. That's an easy case, because if the list is empty, then we just get X. If we insert X into a list Y's, well, it depends. It depends whether X is smaller than Y or not. And if we're going to insert this, well, let's say less than or equals to, if X is less than or equal to Y, then we know that this X has to go on the front of this list, because it's smaller than the first element, and the first element should be sorted. If it's a sorted list, it will be the smallest. So then we just get X on the front of Y's. Otherwise, what do we do? What does the list start with? What's the first element? It must be Y. And where does X go? Does X go next? No, it depends. We need to recursively insert X somewhere into the rest of the list. It doesn't belong at the front of this list, but it could belong anywhere in this list, maybe even at the front of that list, and we find out by just inserting it recursively. We're going to insert X into the rest of the list. Oops, what's going on here? Okay, and it compiles fine. Okay, so we could, yeah, all right. Any questions? No? Okay. Let's do a little test of insertion sort. So we could test insertion sort as it is, but let's test insert, because I think insert is the kind of interesting guy here. It's the meat of the definition. So the claim that we make is that when we insert an element into a sorted list, the result should be sorted. That's really the key property that makes insertion sort work. So we can encode that as a quick-check property. If we have a list, so if X is sorted, well, we could say if X is sorted, then if we insert this into the list, then the result should be sorted. That's fine. The problem with that is that, of course, if we're trying to randomly generate lists and then throw away the ones that are not sorted, we're not going to really, we're not going to get very far. Okay, so what we're going to have to do is sort X's. So what we want to do is we want to insert X into the sort of X's and check that that's equal to sort. Well, we could do this with isort, or we could do it with a built-in sort. But the problem here, as you can see, if we try and test this property here, basically all we're doing is writing down the definition. There's the right-hand side. By definition, this thing is equal to this thing. So all I've done in the property is assert that the left-hand side of the definition is equal to the right-hand side. And of course that's true, because it's a definition. It must be true. So this doesn't actually bias anything. Okay? So in fact what we would really need, what we would like, is a way, so one thing we could do, of course, is to use our external sorting and check that somehow there's a compatibility between the sorting we have originally and this kind. But really what we would like to do in this example, and this is another case where we'd actually like to control the random generation. We would actually like to randomly generate sorted lists and then test this property for those lists. And as I say, at the moment we don't have a good way of doing that, so we'll leave that until next week. You won't have to wait too long. So this is not a very useful test, but it could be done, and it maybe is reasonable. So it's too similar to the definition. Okay. Any questions?